Okay, so yeah, welcome everybody. Can everybody hear me? Would you say yes? Maybe nobody can. Okay, so thank you very much. So if you have any problem of listening to a lecture or any admin problem, please say so, even in the middle of the lecture, okay? So what we will going to cover today is a Dpl algorithm. And it is, one of the, maybe it is in some sense the basis for most of the, highly efficient set solvers in the wild, in the real world. Okay, and then also from the theoretical perspective, DPL algorithm has a very interesting aspect. That's because it combines the idea of a search and then the idea of the logical deduction together in a very nice way. It's quite old algorithm. It's about 50 years old, but still, although there are lots of other improvements in the modern set solvers, this DPLR can still be understood as a core basis of many of these algorithms. It is set solvers nowadays. And then modern set solver is highly efficient. I'm going to show you some graph in the next slide. So it can it can perhaps handle like 10 million clauses, which is a really huge number. And modern set solver also have many other improvements over basic DPL algorithms. So one of the things we're going to talk about is so-called clause learning in this lecture. But there are many other tricks that appears in the modern set solver. So let me just write one thing. So I don't know how many of you heard about Don Knuth. So then so there are some saying which says if you read a book by Don Knuth, something called Art of Computer Programming, then you're gonna get hired in Microsoft programming. And so the book is published like book 1 up to 4 is published, maybe 4A is published. But one of the following books on the art of computer programming, which is, I think, it's going to form a part of either 4B or 4C. That is about, big part of either 4B or 4C is going to be about set solver. So if you want to understand all the details of set solver, actually, you can buy one of the books written by Knuth. What I heard is that in order to write this book, Knuth reviewed many of the existing techniques in modern set solvers. Also, he himself wrote, I think, either 12 or 13 set solvers for himself. And so if you are interested in what's really happening behind the set solver, much more details, even very implementation details, you can look at one of the books by Don Knuth. So that even talk about how to lay out data structure based in accordance with some bits in a computer so as to make some access to computer memory much more efficient. Okay, so let's continue. But we are not going to talk about all the low-level details of the set solver. Instead, we will focus mostly on the basic DPL algorithm and also basic algorithm for doing this clause learning. And as I said in the before, the modern set solver is super efficient. So in my personal experience, I use not set solver, but optimization version of a set solver, which is called max set. And in my applications, that we give a problem which have, I think, either 20 million clauses and about 10 million variables, but that set solver was able to solve such a problem in, I think, maybe in 10 minutes or less than 10 minutes. So modern set solvers are super efficient. That's a bit counterintuitive, especially when you remember what you learned in the algorithm course, because we said set solving, this satisfiability solving for propositional logic is NP-complete problem. So it's a one of the problem which is regarded very hard. But the caveats or some terms and clauses in this NP completeness is that this is a worst case scenarios. In the worst case, this is the solving set with a worst case guarantee is very hard. But in practice, what happens is most of the problems that you can encode into propositional logics do not fall into these worst cases. So modern set solver is able to exploit some common structure in the usual propositional logic formula arising from real world applications. And then they are able to deal with really large clauses. Okay. So what's the basic idea of set solving? Set solving, then Dpl algorithm. So the basic idea of Dpl algorithm is to basically do depth first search. So if you think about set solving problem, so the set solving problem is we are given propositional logic formula in CNF form, and then what we have to produce is either it's unsatisfiable, or this propositional formula will have a propositional variable P1 up to Pn. So we either say it's unsatisfiable, or we have to find an assignment for these propositional variable. So assignment A, which will look like maybe maps P1 to 0, P2 to 1, and so on, such that it satisfies F. So we have to give either unset or the second answer, which is A, find some assignments to the propositional variable that make the formula true. But if you think about the second case, this second case is a bit like solving some search problem. So we have multiple possible A's, which assign different values to P1, P2, and so on. So if we have n variable, there are 2 to the n possible A's, some of which will satisfy A, or maybe, but some of which are not going to satisfy, some of which will satisfy the formula F, some of which will not satisfy the formula F, when formula F is satisfiable. Okay, so among those 2 to the n possibility, we want to find something that will make this hold. Okay, so this can be understood as a search problem, and then you can employ many techniques that you learn for the search. So one of the techniques that you learn is to do depth first search. So then very naive way of doing depth first search is you arrange all the propositional variable like P1, P2, so on up to Pn. And then say the first branch of the depth first search is consider the case where P1 is equal to 0 and P1 is equal to 1. And then because it's a depth first search, you just explore P1 is equal to 0 case first. And then next case is going to be P2 is equal to 0. And then P2 2 is equal to 1, and so on. Then you keep exploring one of the branch using depth first search. If we succeed, great. So if we reach all the way until the end, then we have a complete assignment to all the propositional variables. So we can check whether that assignment make formula F true. If that's the case, we are done. Otherwise, we try something. Try the next guy. But this is a key idea of depth first search. Okay. So that's a kind of very simple idea of depth first search. But the DPLL is a bit like doing deep depth first search. Not exactly, but it has some similar form. But it does a bit more. The one thing that it does is that sometimes it does pruning. So at some point, it realizes actually, if we set P2 to 0, there are no hopes to make this formula true. So then it prunes this search space, and then it only explores P2 is equal to 1. Okay, so that's pruning, right? It's something that's being done in the DPL algorithm. And then the pruning, the key part that enables this pruning is called unipropagation, which I'm going to talk about next. So that involves the what I call deduction step. Okay, so the next thing that it does is it does some search. So say it somehow reached some base case doing the search, but then it realized, I mean, it's a failure case. It doesn't really satisfy F. Okay. So in that case, it does so-called clause learning. So that's what I mean by this conflict clause. So this is the, let's use this. It's a failed path in the depth first search, which avoid pruning steps. So which is unpruned the case of the depth first search, but suppose it failed. Okay, so in that case, it does so-called running the learning algorithm in this case, and then the learning is a bit different from statistical learning. It tried to learn the core reasons why we failed. Okay, and then the outcome of the learning is so-called conflict clause. It's a return a clause C, and then that clause, so that's called a conflict clause. Intuitively, this conflict clause explains why we failed in this search. Okay, I mean there are many reasons for failure, but they try to come up with some most general, not most general, but reasonably general reasons for the failure, and but that encodes that reason in terms of a clause. So the clause can be like a P1 or negation of P3. So because it's a clause, it has this kind of form. So it returns this kind of clause, and then that clause satisfies one property. I'm going to explain to you later about the properties. That clause, when I conjoined with F, it doesn't change its meaning. So see, more logical form. This is really representing F conjoined with C. So conjoining C doesn't change any meaning at all. So it's redundant in terms of semantics, but this C compactly represents some hidden informations or some interesting structure inside F that we discovered from this failed search. Okay. Now, if we add this C, what happens is next time when we backtrack and do some search, this reason C will help us to avoid, will do the pruning more aggressively. The C will provide some further information so that we will never be, we can avoid the same kind of mistake that leads to the the failed path in this here. Okay, so from the failure, we run a clause that C intuitively allows us to avoid a similar kind of failure in terms of algorithm that will help us do more aggressive pruning. So next time when we do the backtrack and then do some search, then because this learned clause C, we may be able to do some more aggressive pruning later. Okay. So that will help to search the satisfying assignment much more efficiently. So this is clause C is called conflict clause. As I said, that we try to encode informally, that try to encode the core reasons for the failure. And then I said, the last clause, the sentence in this slide said that also determines backtracking. That means it will help us to do more aggressive pruning so that we don't have to repeat the same kind of mistake. Okay, just to recap, DPLL for the high level, it's a depth first search with pruning, but it learns from the failed case, and it learns the core reason of the failure from the failed case, and that will help us to do more aggressive or more efficient pruning so that search can proceed much more efficiently. Okay, so let's go to next. So let me, before presenting you the DPLL algorithm, let me give you three main actors. Okay, you can think of this DPLL algorithm is like a movie. So then there are three key components, three main actors that appears in the movie. And the first actor is CNF formula F. Okay, so typically when you think about CNF formula and its satisfiability, you kind of imagine the fixed CNF formula F. That's not the case in the DPL algorithm. So we are given CNF formula F. So F has the form clause 1, clause 2, and clause n. I mean, in the set representation, it's represented as a like set here. Okay, but so that's a given formula, and we are interested in finding the satisfiability of this given formula f. But throughout the algorithm, this formula f gets extended with extra clauses. So especially when you do learning, then this learning will add some extra clause like a D1. And this means from one failed search, we discovered a new clause and that's added. Maybe the next one, D2 is added and so on. So a bunch of things will be added here. But one important bit, which is guaranteed by this algorithm, is that all the things that's added here, they are not really changing the meaning of the original formula. So what we have is that the original formula f, and that's it's a bit difficult. Let's say this becomes f prime because these extra things are added. Original formula f is the same as, is equivalent to the formula f together with all these di's. Okay, so just to say it again, the first actor is a formula which is set to the initial propositional formula, but throughout the algorithm, it's gonna be extended with extra clauses like the D1 up to Dn. But one invariant which this algorithm maintains is that all these DIs are in a sense redundant. They are good for algorithm, for search, but in terms of semantics, it doesn't change anything. So it ensures this equivalence. Okay, so that's a first actor of this algorithm. The second actor is something called valuation. Okay, so this is the states of the search in some sense. Then this valuation is like the one that we talked about before, which is called assignment. We often talk about assignments A before. Okay? It's essentially the same as assignment, except the two things. The first, this is a partial. So our valuations doesn't have to assign values to all the propositional variables. For some propositional variables, it may say nothing. Okay, so it's a partial assignment. That's a first aspect. The second aspect is that it's ordered. Okay, it's not a map. So this sequence aspect is actually quite important. And so maybe you have to say it's a partial assignment. So actually, the sequence of partial assignment doesn't make sense. So let me just get rid of this. So it's a partial assignment, and then it's an order. So before, when we talk about assignment, I just said it's a map. So that we don't have any order that whether P1 is bound first or P2 is bound second. I mean, that kind of information doesn't exist. But in the valuations, we consider that this binding of P1 to B1 is something that's bound first. P2 to B2 is something that bound next, and so on. And this order is not predetermined. I mean, the first one is perhaps determined by this algorithm. So this valuation, one possible valuation look like this: 0, P2 is 0, and P3 is 1. One possible valuation like this. But another possible valuation may look like this: P1, 0, P3, 0, P2, 1. Okay. So these are the two possible valuations. You see that the orders of P2 and P3 are different. So in one case, P2 appears first. The other case, P3 appears first. This matters because what we want to do with valuation is we want to record all the sequence of decisions we made so far in the order that these decisions are made. Okay, or some decisions, but this order really record all these decisions. Okay, so this means P1 becomes 0 somehow, either decided by some choice or forced by what I call unit propagation later. So this is done first. This is done next, and this is done third. That information is recorded here. in the below, it's a P1, this binding is done first by the algorithm, this is done second, this is the third, and that information is recorded. So yeah, so the order is important and it's a partial assignment. And then later, I'm gonna show you actually each of these binding of propositional variable to values, like this guy and this guy. And there are two groups, two kinds of bindings. The one kind is called decision assignment. The other is called implied assignment. Okay, so they are so these bindings are introduced by the algorithm by two different parts of the algorithms, and then one part is, if it's introduced from one part, it's called decision assignment. It's another part is called implied assignment. In the case of implied assignment, we might do some annotate this assignment with some extra information. So I'm gonna repeat this algorithm multiple times so that in the beginning, if you get kind of lost, I hope eventually you get the idea of how algorithm works. But what I explained so far is there are two main actors. One is CNF formula. The second is evaluation. Okay? The third actor, it's not quite an actor, but it is another important part of the algorithm. It's a specialization. So the specialization is we have the first two guys, which is we have a formula F, and then we also have this valuation A. So then we want to simplify this formula F on the valuation A as much as possible. So that's what this specialization is say intuitively. And more formally, what it does is that it compute the value of all the literals which are related to something in A, okay? Because A is a partial assignment. For some literals, we can assign definite value under A, or some literals we can't really assign definite value to under A, okay? So we give definite value under A for some of the literals appearing in F. And then we do the following, which is if a clause after this replacement or after replacing these literals by value under A, if a clause contains the true literals, then we get rid of it. Also, if otherwise, okay, so the clause doesn't contain the true literal, but it contains a false, then we just get rid of this false case. So maybe giving some example is better. So if you have formula F, so if I have a formula F, which is say one clause is P1, not P2. The other clause is not P1 or P3. Okay, so say, assume that we have a valuation which just binds P1 to 1. Okay, so then if I do specialization F under A, then what I told you is by using A, we essentially replace the literals by their values as much as possible. So in this case, we know P1 is equal to 1, so that this guy, these literals will be replaced by 1. These literals will be replaced by 0. Okay? So if a clause contains 1 after this replacement, this entire thing will gone. If a clause contains 0, we just get rid of only this literal. So the outcome of this simplification is going to be just P3. Okay, so that's what this step is saying. I mean, it's something that's obvious if you sit down and think about it a little bit, but it's a sum operation that's being used by the algorithm. And you can also see that implementing this simplification can be done very efficiently. I mean, it doesn't require, it just can be done by a linear search. I mean, kind of in the linear time. Okay, so now next, I want to tell you how the actual algorithm. So I'm going to go through this algorithm multiple times. So if you don't get the idea now, then that's okay. So we're going to eventually get it. So the algorithm takes a CNF formula F. As I said, this formula is going to be changed throughout this algorithm, but it's initially the formula, the first actor in the previous slide, is set to the given CNF formula F. And then output is either some valuation that makes this formula f to true under simplification. Okay. Or we say that I mean, this formula is unsatisfiable. One thing I kind of want to tell you a little bit is that this formula, this valuation A, although my formula F contains propositional variable P1, P2, and P3, maybe this valuation may just assign binding for only P1 and then P2, and then doesn't say anything about P3. But in that case, what this means is you say that whatever value you put for P3, as long as the P1 is bound to 1, P2 is bound to 0, then that's going to satisfy the formula F. Okay, so this gives essentially like however you extend A, they will all lead to the satisfying assignment of F. So that's what's being returned by the algorithm. Okay, so then now how the algorithm works. So you first initialize this so this is satisfying assignment A to the empty list of assignment. Okay, so that's the first step. And the next step, it tried to extend A by using what I call deduction, and then deduction idea. So and then step is called the unit propagation. But here's an algorithm. So what it does is that it simplifies F under A. After the simplification, it may be that some clauses will contain only one literal. So that's what's called unit clause. It's a clause that contains only one literal. If this clause is a conjunction, unit literal means it just say that L should be true. Okay, so that's what this unit literal is telling us. So after simplification, there may be some clause which contains only one literal L. And then we change A so that L is going to be bound to 1. Okay, L should involve propositional variable that's not bound to A. But so we can make an appropriate choice to make this L to 1. So for instance, if on the simplification of A, maybe this CNF formula may contain unit clause like P4 and another unit clause like P7. Okay. So this is a unit clause because it's a clause that contains only one literal. This is another unit clause because it's a clause that contains unit literal P7. So for this case, for this algorithm say that, okay, look at this unit clause, then we're gonna extend A so that use some different notation. So A get extended by adding extra binding. Okay, I'm gonna write it like this. We're gonna add extra binding. That extra binding is which added at the end. That binding say P4 now should be mapped to 0 because that's a way to make this literal to be true. Okay, so that's what's being done. And this process is being repeated over and over again until we end up with this simplified formula that doesn't contain any unique clauses at all. And you can see that this can be also done very efficiently because identifying unique clause, it's very easy. And then setting this value is also very easy. So this part can be done efficiently. Actual implementation does much more efficient implementation of this, but for us, this is enough. Now, the next step is that now, so this, once we finish this while loop, okay, we end up with a formula, but that we end up with the 3 cases. Okay. So we have 3 cases. The first case, is this F under simplification. This will not contain any unique clause at all because of this while loops. But F under this simplification may contain no clauses at all, which means that this F under simplification, F under A, simplified under A, is going to be empty, logically is equivalent to true. So if that is the case, then I mean it's a satisfiable. I mean true is always satisfiable. So we just said stop and said, okay, if f is satisfiable, and then we just return the current valuation a. So this whole thing say that f is true under a. So I mean f is satisfied under a. So we just return a in the first case. So that's not a big deal. The second base case is f. I mean this is not the case, but f contains box, which means the f simplified under A will contains box and perhaps it's a bunch of other clauses, C1, C2, and so on. But logically, that means it contains a false, has this form, and C1, C2, so on. And you can see that the second case is unsatisfiable because one of the clauses is false, it's unsatisfiable. Then we're going to do what I call clause learning. Okay, so I'm going to explain what it is, but let's move on to the next guy. So if either of these cases, so the case number 3, we know f is a simplified f under A is satisfiable. Case 4, we know that simplified f under A is not satisfiable, so it's false. Case this the step 5 say, but there may be some case where we don't know. Okay, so step 5 is neither of the step 3 and step 4. So this is step 5 is neither of that case. We don't know whether f simplified under A is satisfiable or not. So that's our case in some sense. So we don't know. F is satisfiable or so we don't know it's either satisfiable or unsatisfiable. In that case, we invoke some predetermined strategy. So this strategy is a parameter of this algorithm. So we invoke some predetermined strategy that will extend A, this our valuation with additional the assignment. Okay, our valuation. I mean, if we hit this case, that means there are some propositional variables which didn't receive the value under valuation A. So this decision strategy will pick one of such propositional variable P, and then also it will pick the value for that propositional variable B. Okay, and then it will extend A with this binding. So then the new A in this case is gonna become A with this extra binding, which is B. P is now going to map to B. And then the entire thing will go back to step 2 and then repeat this process. So step 3, 4, 5 are in a sense case analysis about what should we do after finishing this step 2. Okay, 3 we are done, 4 we are done in some sense, but we're gonna do what I call close learning. Step 5 we are not quite finished, so then we make some choice. So this is called the search. It corresponds to the search step. We do make some choice for the extra unassigned variables, and then go back to step 2. Okay. Now the remaining part is what should be done for step 4. And for step 4, I'm gonna explain what this learning algorithm, which is based on resolution. But we invoke some algorithm. Okay, so that algorithm will return a clause C. And then we're gonna add that C to F. So F will now, after this step, F will become larger. So F conjoined with the C. Or maybe set notations, it will be like this. Okay. F get extended. Now we do case splits. So then if the C is an empty clause, which means the C is equivalent to false. So then we just stop there and said, okay, it's unsatisfiable. So this clause learning phase might discover that actually, but we have an unsatisfiability proof. So we can stop there and then return unset. Otherwise, we backtrack. So I mean, we backtrack, but until we backtrack to the highest level until the C becomes a unique clause. I think that it's a bit confusing about what this actually means, but I think that if you see on examples, that will becomes a lot easier to understand. So I mean, as you see that step 5, so step 5, make a bunch of decisions for the propositional variable, okay? And then step 3, I mean here, is telling us we have to backtrack or some of the decisions made by this step 5 before until C becomes a unique clause. For instance, if C contains is of the form, okay, if C is of the form, it looks like this, like a P3 or negation of P4 and P5. Okay, suppose C can be of this form. And then say in the previous run, I mean, then we have a assignment A. Assignment have a bunch of decisions made before, but said P4 let me check. Right. So P4 was 1 and P5 was 0. And then a bunch of other things. And then maybe a bunch of other things. And then P3 was 0. And then a bunch of other stuff. So suppose we have assigned this valuation A when you reach this step 3. And then clause C we learn is of this form P3 or negation of P4 or P5. And then assume that this P4, value of P5, and P3 are all determined by, this is step 5 in the previous step of the algorithm. Okay, so when we make this when this is step 5, choose P4 and set it to 1, P5 is set P5 to 0, P3 to 0. Okay, if we reach this case, so then the step 3 is telling us what this is what we should do. So we backtrack a bunch of variables. So we backtrack multiple decisions. So this is all backtracked. And then we backtrack until this whole thing becomes a unique clause under A. So if you, at this point, this is not a unique clause because we have a value for P4, P5, P3 that will make this PA false. So it's not a unique clause. It's just nothing. It doesn't contain any literals at all. But if we backtrack one more, okay, for up to P3 and reach here, then now we know that this is a unique clause because if we simplify this clause under P4 is equal to 1, then this will have a value 0. And P5 has a value, P5 have a value 0. This will have a value 0. So all the things with the value 0 will disappear under simplification. So then the only remaining literals in this clause is a P3. So this is the definition of the unique clause is it's a clause that contains only one literal. So we can get the clause which contains only one literal in this case, which is P3. So we backtrack up to this point, and then we apply the unit propagations. You go back to step 2, and step 2 will do the unit propagation. If we do the unit propagation here, we contain the unit clause P3. So next things this algorithm will do is its algorithm will set P3 to 1. Okay. Now P3 is a unit clause. The unit propagation. The step 2 tells us P3 should have the value. We should make this true. So next time when you run this algorithm again, this will be set to 1. So P3 will be set to 1, and then algorithm proceed from there. So although it's not a full explanation yet, we can kind of see that having this clause like C will forces us to backtrack quite a bit. It kind of and then like, it forces us to prune all the possibilities, which will set P3, P4 to 1, P5 to 0, and P3 to 0. Okay. Anything that have these three combinations will be gone, so that we have to try something different. Okay, so just to sum up, the algorithm take F, return either valuation or unset, and then the key steps are it does this this is step 2, which is keep setting some values of propositional variable based on unique clauses, and then when it's done, it does case analysis. If it's unset, we return unset. And no, if it's a set, we return set. If it's unset, we do what I call learning, and then generate a new clause, and then generated clauses is added, and then that helps us to backtrack. Otherwise, if neither of these 3 or 4, we choose one of the variables and extend the A. Okay, so that's how the basic of the algorithm. Then let me show you the actual execution of the algorithm. Okay. So I'm gonna run this algorithm for this example. Okay, so we have these examples, like say negation of P1. And so this is a formula that we are given. Then I want to tell you how the algorithm works in this case. So in this case, we are given this formula, which is negation of P1 and P1 or P2 or negation of P3 and so on. Okay. So then we start to run this algorithm on this example. So then the algorithm initially sets this satisfying assignment to empty. Then it performed the unit propagation. This is step 2. Okay, this is called unit propagation. So it performed step 2, and then step 2 say simplify the formula F under A, and then pick all the unit clauses. So if we, so let's mix together. So if you simplify F under A, this is the unit clause. So this unit, because of this, let's use this note. Sorry. Okay. So if you the formula F here is P1, P1, P2, P3, P3, P4, P5, and P4, and negation of P5. Okay, so then the step 2 tells us look at all the unit clauses. So this is the first unit clause. So then we extend A. So now after the extension, A will becomes P1 equals to 0. So if you simplify F under A, what's gonna happen is this will disappear. And then this particular literal will disappear in this clause because P1 is gonna bound to 0. Okay? So that's it. Then that's all the things we can do. And that it doesn't contain any unit clauses, this unit clause at all. So we go to this case analysis like 3, 4, and 5. And then it's neither 3 or 4 case. So we fall into the 5th. So in the 5th case step, so what we do in this case is we extend A with P3 to 0. Okay, this is particular choice. This is by 5. And this is by step 2. Okay. Now we do step 5 and we go back to step 2. And then we do further simplifications of the formula F on the both of these assignments. If you do these simplifications, Now, because P3 is equal to 0, this entire thing will disappear. And then now P3 is equal to 0, this will also disappear there. Okay, so at this point, now this is as much as we can do in step 2. Now we do case analysis about the outcomes on this new A. And then for simplify F on the new A, then it's not 3 or 4 case. So we also have to make another decisions by step 5. And yeah, so this case, what we do is P3, 0, and we do P4, 0. So by step 5. So if you do P4 to 0, okay, now further simplification happen. I mean, if P4 is 0, so then this one disappears, this one disappears. Now P5 is a unique clause, so step 2 will force us to set P5 to 1 here. So A gets extended to everything here, 1, 0, P3, 0, P4, 0, and then it set P5 to 1. So by step 2, now by setting the P5 to 1, I mean, this whole thing is satisfied, but this one now will this one will disappear, which means this whole thing will become an empty set, or we use box to notate this. So we denote this. So then after this step 2 is finished, so now we are in a case where F under A just contains box. I mean, in other words, it contains just empty set. So that fall into this case 4. And then in the case 4, we do learning. So I'm not going to tell you how the learning works at this stage, but if we run the learning algorithm that I will explain soon, that learning algorithm will return a clause C, which is P3 or P4. So what this means is the reason why we fail to make F true using A is because we have both P3 and P4 was false. So I mean, the way we should read this C as negated version of C. So if you put negation of C, P3 it's a not P3 and not P4. So that explains why we failed. So the reason why we failed to make F true is because P3 was a false and P4 was a false. So next time we should try search, it's better to make at least one of them to be true. So that's what this extra learned clause tells us. So if we extend F5 with this extra clause C, and if we do backtrack by using step 3, then we will make backtrack until this C become a unique clause. If to make this C to be a unique clause, we have to backtrack up to this point. Okay? Because I mean, we have to get rid of these guys. And then if we backtrack this, and then now go back to step 2, and then use the unit propagations. So then if we have this formula F, and if we simplify on the P1, 0, P3, and 0, and they will have a bunch of clauses together with P4, because it's coming from the clause C that we added, and because P3 is 0, we have a clause that contains P4, and then step 2 will force us to set P4 to 1, so that next time we will explore it where the P4 is bound to 1. I mean, this doesn't exist. And then if you keep doing this, this will lead to a satisfying assignment for this problem. Okay. So that's some explanation of this algorithm. Let's go back and then get this algorithm more. So as I said, this step 2 is called unit propagation, and this is related to the deduction or logical reasoning step. And then step 5 is something sometimes called decision step. That's more related to search. So search is a bit like exploring all the possibility. And this step 5 is related to search. And then modern set solver has a very sophisticated strategy to make right decision here. But we're gonna do something we are not really gonna worry about this step 5 and just make very simple choice. And this learning also will involve deductions. In particular, the particular learning algorithm we're going to talk about will involve resolutions that we learned before. So let's go to each of these steps one by one. But before doing so, we need to introduce some of the terminology. So the two terminologies which I want to introduce here is something related to the states and the decision. So this decisions, assignment, decision variables, and so on. So the notion of states, okay. So the state of the algorithm is really a state of the algorithm. And then the algorithm, in a sense, work on the two kind of pieces of information. The first is a CNF formula F, which is keep getting extended by these clauses that's added through the learning process in the step 4 in the previous slide. And then also the current valuation. Okay, so maybe I have. Okay, so here's an algorithm. So state is really the state of the algorithm, and then so it's a pair of formula and valuations. We say the state is successful if this valuation entails F, which means that on the simplification of F, if we simplify F under A, that will become true. Conflict clause means A it doesn't satisfy F, okay, which means that on the simplified version of A, so actually this is the case, these simplified versions will contain box, which contain contradictions. So these are the two classification of state. And there will be a third kind of state where we don't know, okay? So state is a formula and valuation. It's successful, conflict, or in an undetermined state, okay? It's a 3 possibility. And then the algorithm, Dpl algorithm works by changing this state from one to another. And now for valuation A, okay, we're gonna do some classify each of the binding, here I call it assignment, binding of propositional variable to the value. We're gonna classify them into 2 groups. One is called decision assignments. The other is called implied assignments, okay? Now, if you look at this algorithm, and record the algorithm here, if you see where we extend this valuation, there are 2 places where valuation get extended. The first place is through the unit propagation. The second step is through this decision step. So if something is extended through this unit propagation, it's called implied assignment. And then something is extended here, we call it as a decision assignment. Okay. So these are the 2 distinctions, and that's the only way of extending our valuation. So every binding in our valuation will be either implied assignment or decision assignment. And then furthermore, in the implied assignment, we know that what are the clauses that kind of make us to introduce this implied assignment. That's because of this unique clause. And if you go all the way back to the original F, then there will be a corresponding clause F inside, which becomes this unique clause on the simplification. So we can, in a sense, identify its source. I mean, why we added this implied assignment. And this extra clause will be added whenever we have an implied assignment. So implied assignment, although I didn't show you on the slide before, actually will get annotated with a clause that's that forces us to have this implied assignment. Okay, so just to say it again, we have a states of the algorithm is the formula together with valuation, and then the okay, so then we have a complex state, successful state, and undetermined state. And then for the valuations, each of the binding of propositional variable is classified into either decision assignments or implied assignment. For the implied assignment, we're going to annotate with this clause C, which makes us to introduce this implied assignment in the unit propagation phase. Okay. Now, let's go back and understand this unit, do some practice, or understand a little bit about this unit propagation step. And then the unit propagation step is, it's really simple from the algorithmic perspective. It look at the formula under simplifications. And then if the formula contains unit clause L, so unit clause, which means a clause which contains only one literals, we extend A so that this L is gonna bound to, the value of L becomes 1. Okay. So I think the best way to actually understand it is to actually run it. So I will give you about 3 minutes to solve this exercise. Okay, so here's an example formula F, and then here's the current valuation A. I didn't annotate them with implied or decision, but this is a current valuation A. And then now this F simplified under A has a unit clause P, and then run this unit propagation step. This is step 2 until it finishes. Okay, so that will make many decisions here, and then try to do this. So I will give you 3 minutes to do this. That's okay. P2 doesn't, that propositional variable doesn't have to appear. So it just happened that P2 is not there. So there is no special reason. So Juan asked why P2 is not there. There are no special reason. So in the more optimized algorithm, P2 will not really consider P2, but it just happens that in this example, P2 and P3 doesn't appear. Okay, so I will show you how it works. So let's look at this. Let's consider simplification under A, the formula under A. Then we know that P1 is equal to 1. So right? So this entire thing will disappear because P1 contains 1. And then this everything, all other clauses negation of P1, we will remove negation of P1 because it's going to become false. So we remove them, these guys. And as Juyeon said, I mean, this P2, P3 doesn't appear. So ideally, I mean, in the algorithm, actually, we are not really going to consider P2 and P3, but it happens that this example is P2, P3 just happen to be there. So we don't do anything. For P4, the value of P4 is set to 1. So then none of them contains P4, none of the remaining clauses, but P4 appears in the negative form here. So we're going to get rid of this. Okay, so this is the, I mean, what we get after the simplification. So then this is after simplification, we have a P5, which is a unique, this C1 become a unique clause. So we extend A with P5 to be 1 because we want to, this is step 2 tells us we extend our current valuation to make unique clause to be true. Then P5 becomes 1. So then this entire thing disappears. Now we also get rid of the negative version of P5 for all the remaining clauses. Okay, so then that so if you simplify F again under this extended A, we have more unique clauses. C2 is a unique clause. C4 is a unique clause. So now let's pick C2. And then C2 as a unique clause, we have a P6. So we extend our valuations to map P6 to 1 because of this unique clause. If we simplify again, the C2 now gone. For C3, the negation of P6 disappears. Now at the last step, we have a C3 and C4, and then there's both of them are unique clause. We pick just one of them, which is just C3, and we extend it with P7 to 1 because of C3. Okay, we can say C3. This one was C2. Yeah, it was C1. Okay, so then on the C3, this disappears, but this is C4. I mean, yeah, so this disappears, but this becomes the empty clause. Okay, so after all entire simplification, we end up with F simplified under this final A will be an empty set which contains a box. So we have to do some cross learning here. Okay. And right. So this is the outcome. Maybe the same or different, but it's essentially the same thing we're gonna get. And then we end up with a contradiction. So we have to run this step 4. Okay. So let me just mention one kind of high-level comments on the step 2. Step 2 is a bit like we are not searching. If you understand search as just making some decisions or some choice among multiple possibility, step 2 is a bit different because step 2 is really reasoning about the problem F, and then see that what are the consequences of all the decisions that I made so far. And based on this reasoning, we extend our, we said, okay, because of these other consequences, something that contradicts these consequences will never make it. So we just follow what these consequences say. So step 2 is it's something that involves this type of logical reasoning instead of search. Okay. Now the important bit of this algorithm and also a bit confusing part of this algorithm is how this step 1 is working. So I'm going to explain a little bit today and maybe next week, explain it a bit further. And then this step, which is correspond to this step 4 of the algorithm, it's okay. So it returns when we reach a conflict state, which is a state which means the simplified formula contains a box. This gets invoked, but this part is kind of run, and then that part will invoke some algorithm, and that algorithm will return this clause C. And here's that's something that we have this algorithm, this closed learning algorithm has to satisfy. And then it has to satisfy these three properties. Okay. So I'm talking about this step 4 and then this learning procedure that's mentioned in the first part of step 4. And that first step, this learning algorithm has to satisfy these three things. First, the clause that we return, okay, that shouldn't change the semantics. This is about something that I already told you. I mean, in other words, in what with this, in other words, F should be logically equivalent to F conjoined with C. Okay? So C is, in a sense, redundant clause, but it's going to be useful for solving satisfiability problem. Second property, which I didn't explain to you before, is that it has to be a so-called conflict clause, which means that every literals in C should be false under the current assignment A. Okay, so if current assignment A maps P1 to 0, P2 to 0, and P3 to 0, then C with so P1 or P3 is okay. So this satisfies the second requirement because every literal that appears in C has a value false under A. Okay, so this is okay, but C with P1 or negation of P3, this is not okay because this clause is satisfied, it's true under A. Okay, the reason that this two is more related to why we are introducing this C. We are introducing this C to capture the idea that why this assignment of the valuation A doesn't really satisfy F. So C, its goal is to capture the essence of why A doesn't satisfy F, which means that if there's a C itself shouldn't be a clause, which is so there's a second requirement to say the kind of one way to capture this essence is to introduce some clause which is false under A. Okay, so then that immediately tells us why A doesn't satisfy F. These two conditions are true. C is redundant. On the other hand, to check A doesn't satisfy this formula F, we can immediately check this by just checking A, doesn't satisfy C because it's a conjunction. If A doesn't satisfy C, it doesn't satisfy the entire thing. So this second requirement tells us, is it really saying C should capture why A doesn't satisfy F? Okay, so that's a second requirement. The third requirement is more related to also our reason for introducing C. The third requirement is that every propositional variable that appears in C has to be a decision variable. So they are the ones whose bindings, like this, right? So like binding under A, like these two guys, these bindings should be introduced by this is step 5. Okay. So if this, let's say P3 is actually introduced by this step 2, so then although this is a conflict clause, this is something that we don't want to include in here. So every propositional variable should be a decision variable. In other words, all their bindings under A should be introduced by 5. Okay. So then the question, so that to sum up, the three requirements this closed learning algorithm has to satisfy is that it has to return a clause which doesn't change the meaning. So that's a step 1. Step 2 is that C should be unsatisfiable under A. So that should be a conflict clause, should be unsatisfiable under A. So it give a immediate reason why C doesn't satisfy the formula F. The third, C should only talk about decision variables, the variables whose binding in A are introduced by this is step 5 of the algorithm. Okay. So I have about 4 minutes, so I'm gonna give you the algorithms, which I'm gonna explain more next time. So then the question becomes how we can design such an algorithm. And here's an algorithm, one algorithm that you can do it using resolution. Okay. So the algorithm works like this. When the algorithm gets invoked, we are in this situation. F simplified under A contains a box. It contains a contradiction. So the algorithm works backward. So algorithm first pick the original clause of F, which has become this box under the simplification. So you find a clause k plus 1, okay, which becomes a box on the simplification when we simplify this formula F under A. Okay, so you pick one clause there. So then you can see having F is logically equivalent to F conjoined dk plus 1. That's because, I mean, dk plus 1 is already in F. Okay. Also, so let's think about the three considerations or three criteria that we have to meet. This is already true. The second thing is that we should say A shouldn't satisfy dk plus 1. That's also true because we pick dk plus 1, which will become box on the A. Okay, so that's exactly the second conditions, which correspond to the second requirement before. But the third requirement, which say all the variables in dk are only decision variables. Okay. Decision bars only. This will not hold. I mean, in general, this property is not going to be true in the beginning. So the remaining part of the algorithm is, in a sense, transform this dk plus 1 by going through all the propositional variables backward according to this order, going through the propositional variable backward from, and then it ensures it transforms dk plus 1 such that 1 and 2 are still true, but step 3 becomes more and more true. Okay, step 3 in general is not true in the beginning, but by going through this backward induction, it becomes more and more true. And now what's the key step? So the key step, I mean, the actual algorithm step consists of these two things. The first, we look at the binding of di get bound to bi. So we are currently in step I, and try to transform di plus 1 to di. And if a pi doesn't really appear in di plus 1, then we don't care, because all we care about is this step, making sure step 3 is true. And the propositional variable di may be decision or maybe not decision variable, but if it doesn't appear, we don't care. So in that case, we can skip. If pi, so this is the second case, but if pi the decision assignment or pi the decision variables, then again, we don't have to worry about it because the step 3 is true for pi. So in that case, we just set pi to di plus 1. Otherwise, so pi appears in di plus 1, and also it's an implied assignment. Okay, so pi appears d plus 1 in implied. This means that, okay, di plus 1 contains either pi or its negated form, and then this, because it's an implied assignment, this means the ci will contain, in this case, either pi or negation of pi. But it's, because it's a conflict clause, this di plus 1 is a conflict clause. It's always the case that we have, either this match. So if this pi appears in di plus 1, negation of pi appears in ci, or this match. If negation of pi appears in di plus 1, pi appears in ci. So we can apply the resolution. So we apply the resolutions, and in the first case, we get rid of these two and just combine, take a union of these things that will give us, di here. And do the similar thing for the other case. Okay, so that's the how algorithm works. I'm gonna go through this part, the cross learning part, and then I'll explain to you about why this actually is correct in the sense that it satisfies our 3 requirements. Okay, so that's it for today, and I'm gonna stay here for about 5 minutes, and if you have any questions, you can ask me. Okay, so thank you.